Nitrogen and hydrogen will mix in a 1:3 mole ratio and left to reach equilibrium in a flask at temperature of 550 Kelvin. The equation for the reaction between nitrogen and hydrogen is shown. There's the equation. When equilibrium was reached, the total pressure in the flask was 150 kilopascals and the mole fraction was 0.0. So the partial pressure equal to mole fraction times by total pressure. So for partial pressure of NH3, it's going to be 0.0 times 150. 120 kilopascals. And now we know the total is 150, so the remaining pressure is going to be 150 minus 120, 30 kilopascals. And that's going to be shared between nitrogen and hydrogen. And you might be wondering, how do we know like how much nitrogen gets, how much hydrogen gets? Well, we know that, there we go, we know that it's a 1:3 molar ratio, so we're going to do this divided by 4, because 1 plus 3 is 4, and therefore we get the partial pressure of nitrogen is going to be 0.25 times by 30, 7.5, and therefore 30 minus 7.5, we get 22.5 partial pressure of hydrogen. So partial pressure is equal to mole fraction times by total pressure, which is a pretty simple formula to remember. Mole fraction times by total pressure. So this bit can trick people out. The mole ratio and then remaining, and then you got to share it, and then you get this with 3 marks. Give an expression for the equilibrium constant for this reaction, where Kp is going to be equal to partial pressure of NH3 ammonia squared, products over reactants, N2 partial pressure N2 squared times by partial pressure of H2. Those p's should be a bit smaller, but it should be fine, or H2 cubed. And remember, Kp curly brackets. However, if it's Kc, then it's square brackets. But we're not doing Kc, it's Kp, so it's curly brackets. Then it says 2.3, in a different equilibrium mixture under different conditions, the partial pressure of these gases are shown in table 2. Calculate the value of the equilibrium constant for the reaction, give its units. Well, we know Kp equal to the partial pressure of NH3 squared. So it's going to be NH3 1, don't forget curly brackets, 1.1 times by 10 to the power 3 squared, all over partial pressure of N2, N2, 1.20 times by 10 to the power 2 times by H2, 1.50 times by 10 to the power 2 cubed. So we've got products 1.10 times by 10 to the power 3 squared, 1.20 times by 10 to the power. Ooh, made a mistake. No, I didn't. I don't know why I wrote squared here. Should not be squared. Silly mistake. Times by H2 cubed. And therefore we'll get Kp as curly brackets 1.1 1 times by 10 to the power 3 squared over 1 over 10 by 10 to the power 3 squared, 1.20 times by 10 to the power 2 times by 1.50 times by 10 to the power 2 cubed. 2.98 times by 10 to the power minus 3. And the units, well, it's going to be, well, what is it, kilopascals? Yeah, kilopascals. So it's going to be kilopascals squared, kPa squared all over kPa to the power 4. And that will give me 1 over kPa squared, which is just going to be kPa to the power minus 2, because the power of 2 is in the denominator, so it's going to be negative. 2.4, the enthalpy change of reaction is minus 92 kilojoules per mole to the power of minus 1. State the effect, if any, increase in temperature and value of Kp for this reaction. Justify your answer. Well, effect on Kp. Well, if the enthalpy change for the reaction is negative, if we increase the temperature, if it's, well, it's negative, so it's going to be exothermic. And if we increase temperature, it's going to shift in the endothermic direction, and therefore there's going to be more reactants than products. And therefore, if we do increase the temperature, it's going to decrease. Yeah. So just simple decreases. Why does it decrease? Well, because forward reaction is exothermic. Therefore, increasing the temperature will cause equilibrium to move in endothermic direction. Okay, left direction. Why does it do this? To oppose the increase in temperature. Think about it. Forward reaction, let's say it's negative. What was it? Negative minus 92. Obviously, for a different reaction, but same, you know, N2 plus 3H2 to form 2NH3 ammonia. If it's negative, therefore the forward reaction is exothermic. Therefore, if we increase the temperature, equilibrium is going to shift left hand side to oppose increase in temperature, this is the endothermic, so it's going to shift to the left hand side to oppose increase in temperature. Therefore, there's going to be more reactants over products. Therefore, let's say you've got the products is 1 and the reactants, think about it, 1 over 2, 1 over 4. Which one is a bigger number? Obviously this one. And you can see that when we increase the denominator, the number becomes smaller. If we have the same numerator, we increase the denominator, the number is going to become smaller. We go from 0.50 to 0.25. Therefore, same with Kp. We increase the temperature, it's going to equilibrium shift in the endothermic direction, the left direction, oppose increase in temperature. Therefore, we're going to have more reactants over products. So products is going to stay the same. That's products. This is reactants. That's products. That's reactants. Products are going to stay the same, but the reactants is going to increase. And if you're dividing by a bigger number, the equilibrium value number you're going to be left with is going to be a smaller number. So hopefully that made sense for you guys. Once you get your head wrapped around it, it's pretty simple. And that is the end of question 2.